All right, hello everybody. Mr. Spear back with another test review solutions video. Please watch this. If you watch this and you understand this, you will get a good grade on the test. I mean, this is exactly what we're going to be doing. All right, so watch this, watch it the night before, the morning of, whatever you can, but watch this and really try and understand it. Here we go. First question. Is the above chart exo or endothermic? Well, let's look. The reactant has more energy than the product. If the reactant has more energy than the product, that means that energy is lost. If energy is lost, then it is exothermic. Okay, we just talked about this. The product has less energy than the reactants, right? It's a lower down. Right here, less. This means less energy. This is a positive or negative delta H. Delta H is the change in energy, or change in heat really, so that it will be a negative delta H because it is going down, right? This delta E is the same as the delta H right here. Boom, delta H. A catalyst would make this require more or less activation energy. Well, we can look right here. This gray line is the uncatalyzed reaction, and this black line is the catalyzed reaction. So this obviously shows us that this would require less activation energy. All right, so I already worked out the second half. 12 grams of hydrochloric acid dissolved in 270 milliliters of water would be a blank molar solution. To begin, we need to change grams into, let me turn the light on. There we go. We need to change grams into moles. And to do that, we just divide the given number by the proper number. We get an amount of moles. And then to find the molarity, we do 0.33 over 270 milliliters, right? Because we're given milliliters, is equal to X over 1,000. That's going to give us our molarity of 1.23. And then down here, 35 grams of salt and 1.2 liters of water. We're going to change 35 grams into moles. Remember, we always want to deal with molarity in moles. So that gives us 0.6 moles. And since we're given liters, we could just do 0.6 divided by 1.2, and that's going to give us 0.5 molarity. You should be very good at this because we've been doing this all last week as well. So for honors, right here, we're dealing with 200 milliliters of 3 molar calcium sulfur solution is diluted with 45 milliliters of water. What is the new molarity? First, we want to find out how many grams of calcium sulfide were in this reaction. So we do our molarity multiplied by the proper number of grams multiplied by the liters. And in this case, since it's 200 milliliters, it's just 0.2 liters. So 3 times 72 times 0.2 is going to give us our weight that we used in the beginning, the weight of our initial solutes that we put in there. So 3 times 72 times 0.2 is going to give us our initial weight. Now 43.2 divided by 72, that's going to give us the amount of moles we have, right? And we can use this finally to figure out our new molarity of the solution. We began with 200, we added 45, so we do 0.6 over 245 is equal to X over 1,000. We solve this out and we get 2.45 molar. Okay, so for Henry's law, solubility and pressure of gases dissolved in water are directly or inversely proportional. So, for Henry's law, solubility and pressure are directly proportional. The more pressure, the more solubility. And that's the fact. And that's represented here, right? The more pressure, the more solubility. And we can see that in action right here by this question. If 0.002 grams of gas are dissolved in 1 liter of water at 1 atmosphere pressure, how many grams could be dissolved at 1.2 atmospheres of pressure if the temperature didn't change? Well, we just write this out. 0.002 over 1 is equal to S2 over 1.2. And we just multiply 1.2 by our initial solubility, and we end up with 0.0024 grams per liter, which is a little bit higher because of the larger pressure. All right, so let's read this phase diagram. 70 bars of pressure and negative 75 degrees Celsius would be what phase of matter? So let's see, here's negative 75 and here's 70. So it would be right there. That is solid. I'll go ahead and mark that as 1. 50 bars of pressure at negative 25. It's liquid. Let me go ahead and mark that. That's number 2. Going from a solid to a gas is called sublimation. That's just vocabulary. Sublimation. What would be the container at triple point? So I'm thinking what would be in the container at triple point? It would be solid, liquid, and gas at the same time. And then what are the first 2 laws of thermodynamics? Law number 1, this is just important to know. So law number 1 is heat. I'm going to just write it out. Heat cannot be created or destroyed. It is transferred. And the second law of thermodynamics is all things tend to turn to chaos, or all things tend to turn to chaos/disorder, known as entropy. So first law is that heat is neither created or destroyed, and second law is entropy is the measure of disorder, essentially. That's what you need to know. Exothermic reactions tend to have a positive or negative delta H. That should be a delta H, and it would, if we can reference actually the beginning page, let's see, the reactant, the product, this is exothermic, they tend to have a negative delta H. So a negative. Endothermic reactions take in or give off heat. Endothermic reactions take in heat. That's why they feel cold. It absorbs the heat. Which feels hot to the touch, exo or endo? We just discussed this, but exothermic, since it is releasing heat, since it's releasing energy, it feels hot. If a reaction occurs and the product contains more energy than the reactants, the reaction was endothermic. Right? If it ends up with more energy than it started with, that means it took in the heat, which means it was endothermic. Here we go. How much energy is required to heat 45 grams of water from 40 degrees Celsius to 43 degrees Celsius? This is dealing with our Q equals MC delta T, which is Q equals MCAT. So let's look at this real quick. All right, so we have our mass, the specific heat of water, 4.18, and then the total change, the change in temperature, and this equals out to 564.3. 564.3, and remember this is joules. All right, what is the specific heat of a 200-gram substance that loses 1,200 joules of energy by cooling off only 4 degrees? Let's find out. So, we are just going to divide 200 times 4. 200 times 4 is 800. We're going to divide this over. So it's going to be 1200 divided by 800, which means our specific heat is 1.5 joules per gram degree Celsius. All right, something with a high specific heat holds more energy and heats up more slowly. True or false? That is true. Lastly, here we go. We are reading a solubility graph here. Being above the line on this chart means the solution is supersaturated. Being below the line means it is unsaturated. And being on the line means it is saturated. How do you supersaturate water with sugar to make sweet drinks? Heat. So, I wrote that wrong. Heat up the water. So the solution accepts more sugar, then cool down the solution. Right? So if we heat up the water, we can look at, I know this isn't sugar, but we can just look at this right here. Or actually, let's look at calcium chlorate so we can actually see the temperatures. If we heat up the water to, say, 60 degrees Celsius, we only need 60, we can add almost 25 grams, and then we cool it back down to room temperature. It feels super sweet because we don't lose any of this calcium chlorate, and in this case, we want to look at sugar, but we don't lose any of that. It stays here at 20 degrees Celsius, right? And really, it's supposed to be right here, so that's really super saturated. So that's the way you do it. You want to heat it up. You heat up the water so the solution accepts more sugar, and then you cool down the solution. That's how you supersaturate. All right, any questions? Just go back and rewatch. Please, please watch this and understand this. You will get a good grade if this makes sense. Write any questions. I'll be watching it all night long. Good luck.